In this project, we will demonstrate import from Dymola physical analysis component models of the pump system and connecting them together in SysML to the broader architecture of the system, tracing to requirements, performing simulation and automatic requirements verification and issues mitigation with updated system logic. So we will use FMU functional mockup units which are based on functional mockup interface standard, perhaps the most popular simulation tool interchange standard, supported by more than 100 tools already, which allows to export executable models to other tools and to execute them without original or with original models. Dymola supports the standard very well. They are part of the community leading the standard, and Cameo Systems Modeler also supports the standard on an import side to be able to execute the models in co-simulation mode. Now, what we are going to do here, we are going to demonstrate how that import works. So when you have FMUs exported from Dymola, you can just take one and drag and drop it to block diagram. You get the block, and this block is calling binary code behind FMU, which is zipped file. Now we will delete this one and use those already imported too, but pretty much the same we could get. And you see there's less properties in those previous blocks which I imported before, because you can delete the properties which you don't need, and that speeds up the model execution. Now, once you imported both FMUs, you see the ports where flow uh, ports. Now we see here in the block, we connected those ports that controller would provide frequency and would get level of the tank, water tank, and frequency is controlling the pump to switch it on and off. And the valve property is here not connected to anything, so it's manually controlled. Now we can execute this model and see what happens. Let's run it. And we can track any properties during execution. As we can see here, we can see those properties. And also we can monitor those properties here. So we see that water level is increasing. And if we want to decrease the water level, from time to time we can open valve manually. See that water levels start decreasing. This tracks water level, but it's a very small difference here. Here we see frequency of the switch from controller, and based on that frequency, the valve controller switch off and on pump. So if I can close the valve, water should start increasing. So we now see that water starts increasing. Once the set point is reached, here we see set point. Okay, so now let's do a couple of more things. So now, first of all, let's trace the requirements. So that's kind of very simple thing. We can just get those requirements from many different sources using PreCAF standard import from Novia, using copy paste, import from Excel, CSV format. That doesn't matter. We can then trace the requirements from the architecture side. And using natural language analysis, we get the automatically converted requirements to constraints. We see that the property level is less than 2.1 and property level is shall be more than 2.19, right? This is based on this glossary, which automatically converts, here we have It automatically converts text to comparison and takes the property name from this value property or the flow port and the number in the requirements. So if requirements would change, this constraint would change. So we can check that. Like for example, if I put here 5.1 and go to constraint, I would see this 5.1, right? So this dynamically updates. So it's a very nice way to improve the quality of requirements. Now let's execute this model again and let's see what happens now. So now we see that the requirements, the properties are changing, model is executing, but also we see that this property satisfies requirements or not, right? So if it is green, then satisfies requirements, is satisfied. If it becomes red, we see even which requirements are not satisfied, right? And I can, open valve at any moment, right? But let's wait because we have requirement that it should be less than this number, right? 2.21. So what happens when the requirement is not satisfied? We'll see in a moment. So we see that the requirement got not satisfied, but logic doesn't prevent that, right? So we get system logic in the system perspective, right? Incorrect, right? So based on those physical components which we brought in from the Dymola, like now let's try to update the logic of the system that a valve would open automatically and would prevent requirements to fail, right? So let's stop it and let's create the valve block, which I already have here. So let's say parts, I have this valve block here, and then create a couple of properties, valve level, because I want that based on the level, valve would be switched on and off, and then connect those properties to take them from the different places. So for example, the valve should come from this, update this port, and level should come from this port, right? So that kind of behavior we can perform connections we can create in internal block diagram. Here we have this block diagram where we connected those, and now I will connect my level to this here and my valve to this one. Now I can create my state machine right in this controller block, which on a valve on level more than 2.205 switch valve on, and after 20 seconds switch valve off. I could put here maybe 30 seconds. Who knows what's the best number? Also, I can put the base, could put the specific level, right? When level drops to specific one, but I could use time event also. And here we updating valve property, right? So now let's execute this system with the state machine of the new valve controller. Let's run it and see what happens. And I put 30 seconds to react, to switch valve off. See what happens. See that new valve properties are updated, right? And now valve is off. If we will reach this 2.205, it should switch on, and we will prevent that the requirement would not be satisfied if we are correct with this logic. Okay, so it worked, it switched here, right? So it's okay, right? It works as expected. Now if we will wait 30 seconds, it should switch back. And the execution time could be increased in order not to be actual time. And we did that, we slightly increased it, but still we want to monitor behavior until we debug it. So we want that it would be as fast as we want, but not too fast. So we always see here execution clock, right? And we see that we reach the limit, right? So we reach the limit of another requirement because this executed too slowly. So valve was open too long, right? So maybe we should just stop it and then switch the duration to 20 seconds. That valve would be open only for 20 seconds. From the So let's come back here. And now let's see what happens. And now let's try to track the execution and record this in the sequence diagram. So we can record this execution. We see here, we are recording execution as the sequence diagram. Every component, every property change gets recorded, unless we will specify that we don't want some of those. So for example, maybe we just want timestamp on the state change, but we don't want timestamps on the properties change and don't want property changes at all, right? So this kind of behavior could be specified in the configurators. We see the sequence diagram gets created here. Okay, still open. And we see soon it will be closed. So we switch to closed. So that's it. So we can then do a couple of more things. We can always create those configurators to execute the system logic to monitor the system logic in sequence diagram using this one, sequence record as a sequence diagram execution. And then we can configure here, for example, to ignore the recorded object pairs, values, ignore signals, lifelines, record state changes, value changes. So we say false for value changes, yes for state changes, or timestamps, yes. Now we can execute this model and see what happens. So now we'll see only state changes. And shows state changes at what time it was changed, right? So valve controller at time 0 is closed, the initial state, right? Let's continue execution. And you remember that reached, it's open, right? So at 17 seconds, and then we will see that in 20 seconds, it will switch to close if we will wait for that time. So we can do import from different tools. Dymola is the primary tool for FMUs export. And we can do different FMUs with the development of new components. We can compare them, do trade-offs from the system architecture perspective, gain trace to requirements, and then really automate the requirements verification with the updated system design. So designers works on the specific physical models. We work on the requirements traceability, and we see that those specific physical models in the system perspectives will still work and will satisfy requirements. So we see here it 20 seconds and it switched to close. So very precise. We know the duration and we know that it will work with this kind of controller.